The National Electrical Code requires that a generator be grounded to a ground rod at the generator location. The size of the bonding conductor is determined based on the size of the equipment grounding conductor. NEC Article 250.30a states that the equipment grounding conductor shall be connected to the generator frame at any convenient point within the enclosure or on the outside of the enclosure of the generator. NEC Article 250.66 of FIVB says where an equipment grounding conductor is installed with a grounding electrode conductor on a common raceway, the equipment grounding conductor shall have an insulation rating equal to that of the grounding electrode conductor. NEC Table 250.122 specifies the minimum size of equipment grounding conductors based on the size of the circuit conductors. The equipment grounding conductor originating from the generator is typically sized according to Table 250.122. The bonding conductor must be the same size or larger than the equipment grounding conductor. For a 1200 kilowatts generator with a 480 volt system, Table 250.122 indicates that a number 4 American wire gauge copper conductor is required for the equipment grounding conductor. Based on the NEC requirements and the information provided, a number 4 American wire gauge copper bonding conductor would be appropriate for the described situation. To elaborate further on grounding and bonding requirements for generators, let's delve into the specifics of the NEC articles and tables mentioned. Firstly, understanding the function of grounding and bonding is crucial. Grounding creates a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices like circuit breakers or fuses. Bonding, on the other hand, ensures that all metallic parts of an electrical system are at the same electrical potential, minimizing the risk of electric shock. NEC Article 250.30e emphasizes the direct connection of the equipment grounding conductor to the generator frame. This connection is vital for creating a solid ground reference for the generator and any equipment connected to it. The point of connection can be either inside the generator enclosure or outside, as long as it provides a reliable electrical connection. NEC Article 250.66 of FIVB addresses a specific scenario where the equipment grounding conductor and the grounding electrode conductor are installed in the same raceway. In this case, the equipment grounding conductor must have an insulation rating equal to that of the grounding electrode conductor. This requirement is to ensure that the insulation of the equipment grounding conductor is sufficient to withstand any potential voltage stress that might occur during a fault condition. NEC Table 250.122 is the key resource for determining the minimum size of the equipment grounding conductor. The table is based on the size of the overcurrent protective device protecting the circuit conductors. For example, if the overcurrent protective device is rated at 400 amps, Table 250.122 would specify the minimum size of the equipment grounding conductor. Now, let's consider the specific example of a 1200 kilowatts generator operating at 480 volts. To determine the appropriate size of the bonding conductor, we need to follow these steps. Firstly, calculate the full load current of the generator. The formula for calculating the full load current of a three-phase generator is kilowatts times 1000 divided by 1.732 times volts times the power factor. Assuming a power factor of 0.8, the full load current would be 1200 times 1000 divided by 1.732 times 480 times 0.8, which equals approximately 1804 amps. Secondly, determine the required size of the circuit conductors based on the calculated full load current. Consult NEC Table 310.16 or other relevant tables in Chapter 3 to select the appropriate conductor size. The conductor size must be sufficient to carry the full load current continuously without exceeding the conductor's ampacity rating. Thirdly, once the circuit conductor size is determined, refer to NEC Table 250.122 to find the corresponding minimum size of the equipment grounding conductor. For instance, if the circuit conductors are sized at 500 kilocircular mils copper, Table 250.122 would indicate that a number 1 American wire gauge copper conductor is required for the equipment grounding conductor. Lastly, ensure that the bonding conductor is the same size or larger than the equipment grounding conductor. In this example, the bonding conductor should be at least a number 1 American wire gauge copper. It's important to note that the minimum size requirements specified in the NEC are just that, minimums. In some cases, it may be necessary to increase the size of the equipment grounding conductor or bonding conductor to provide a lower impedance path for fault current. This is especially true in systems with long conductor runs or where sensitive electronic equipment is being used. Additional considerations for grounding and bonding generators include the type of grounding system used. The NEC recognizes several types of grounding systems, including solidly grounded, impedance grounded, and ungrounded systems. The type of grounding system used will affect the specific grounding and bonding requirements. For example, in a solidly grounded system, the neutral point of the generator is directly connected to ground. In an impedance grounded system, an impedance, such as a resistor, is inserted between the neutral point and ground. In an ungrounded system, there is no intentional connection between the neutral point and ground. Each type of grounding system has its own advantages and disadvantages, and the selection of the appropriate system depends on the specific application. Another important consideration is the location of the generator. If the generator is located outdoors, it must be protected from the elements. This typically involves installing the generator in a weatherproof enclosure and providing adequate drainage to prevent water from accumulating around the generator. The grounding electrode system for an outdoor generator should also be designed to withstand the effects of corrosion and other environmental factors. In addition to the NEC requirements, there may be local codes or regulations that apply to the installation of generators. It's important to check with the local authorities to ensure that the installation complies with all applicable requirements. Proper grounding and bonding of generators is essential for ensuring the safety and reliability of the electrical system. By following the NEC requirements and paying attention to the specific details of the installation, you can minimize the risk of electric shock and equipment damage. Let's elaborate further on the practical application of these concepts. Imagine a scenario where a 1200 kilowatts generator is installed at a remote cell tower site to provide backup power during grid outages. The generator is housed in a weatherproof enclosure and connected to a transfer switch that automatically switches the load from the utility grid to the generator when a power failure occurs. Firstly, the installation must comply with all applicable NEC requirements, as well as any local codes or regulations. This includes obtaining the necessary permits and inspections. Secondly, the generator must be properly grounded and bonded. A ground rod should be driven into the earth near the generator enclosure, and a grounding electrode conductor should be connected from the ground rod to the generator frame. The size of the grounding electrode conductor should be based on the size of the generator service entrance conductors as specified in NEC Table 250.66. Thirdly, the equipment grounding conductor should be connected from the generator frame to the transfer switch enclosure. The size of the equipment grounding conductor should be based on the size of the circuit conductors, as specified in NEC Table 250.122. In this case, since the generator is a 1200 kilowatts, 480 volts unit, the full load current is approximately 1804 amps. Assuming that the circuit conductors are sized at 500 kilos circular mils copper, the equipment grounding conductor would need to be at least a number 1 American wire gauge copper. Fourthly, all metallic parts of the electrical system, including the generator enclosure, transfer switch enclosure, and any conduit or raceways, should be bonded together. This ensures that all metallic parts are at the same electrical potential, minimizing the risk of electric shock. Bonding can be achieved by using bonding jumpers or by using listed bonding connectors. Fifthly, the neutral conductor of the generator should be connected to the grounding electrode system at the generator. This connection should be made at a single point only to avoid creating multiple neutral to ground connections which can cause circulating currents and other problems. Sixthly, the generator should be tested and inspected to ensure that it is operating properly and that all grounding and bonding connections are secure. This includes performing a ground impedance test to verify that the grounding system is effective in providing a low impedance path for fault current. By following these steps, you can ensure that the generator is properly grounded and bonded, providing a safe and reliable source of backup power. It's also important to remember that grounding and bonding requirements can vary depending on the specific application and the local codes or regulations. Always consult with a qualified electrical engineer or electrician to ensure that the installation complies with all applicable requirements. Proper grounding and bonding is not only essential for safety, but it can also improve the performance and reliability of the electrical system. A well-grounded system can reduce electrical noise and interference, protect sensitive electronic equipment from damage, and improve the overall efficiency of the system. In conclusion, understanding the principles of grounding and bonding and following the NEC requirements is crucial for ensuring the safe and reliable operation of generators. By paying attention to the details and consulting with qualified professionals, you can minimize the risk of electric shock and equipment damage and maximize the performance of your generator system. Further consideration should be given to the type of loads being served by the generator. Sensitive electronic equipment, such as computers and communication systems, may require additional grounding and bonding measures to protect them from voltage transients and other electrical disturbances. This may involve using shielded cables, surge suppressors, and dedicated grounding electrodes. Additionally, the generator's automatic voltage regulator, or AVR, plays a role in maintaining stable voltage output. The AVR should be properly adjusted and maintained to ensure that the generator provides a consistent and reliable power supply. Regular maintenance of the generator is also essential for ensuring its long-term reliability. This includes checking the oil level, coolant level, and battery charge, as well as inspecting the engine for any signs of wear or damage. The generator should also be exercised regularly to keep the engine lubricated and to prevent fuel from deteriorating. The frequency of maintenance will depend on the generator's usage and the manufacturer's recommendations. In addition to the technical aspects of grounding and bonding, it's also important to consider the human factors involved in operating and maintaining generators. Personnel should be properly trained on the safe operation of the generator and the potential hazards associated with electricity. Warning signs should be posted to alert personnel to the presence of high voltage and the need to follow safety procedures. Emergency procedures should be in place in case of a generator failure or other electrical incident. These procedures should include instructions on how to safely shut down the generator, isolate the electrical system, and contact emergency personnel. By addressing both the technical and human factors, you can create a safe and reliable generator system that provides backup power when you need it most. Also, it is important to document all grounding and bonding connections. This documentation should include the size and type of conductors used, the location of grounding electrodes, and the results of any ground impedance tests. The documentation should be kept in a safe place and readily available for future reference. Furthermore, it's important to understand the difference between grounding and bonding. Grounding provides a path for fault current to return to the source, while bonding ensures that all metallic parts are at the same electrical potential. While both grounding and bonding are essential for safety, they serve different purposes. Grounding is primarily intended to protect against electrical shock, while bonding is primarily intended to prevent electrical fires. In some cases, it may be necessary to use both grounding and bonding to achieve adequate safety. For example, a generator enclosure may be both grounded and bonded to ensure that it is at the same electrical potential as the surrounding equipment and to provide a path for fault current to return to the source. It's also important to be aware of the potential for stray currents in grounding systems. Stray currents can occur when there are multiple paths for current to flow, such as when there are multiple grounding electrodes connected together. Stray currents can cause corrosion of metallic equipment, as well as interference with sensitive electronic equipment. To minimize the risk of stray currents, it's important to use a single-point grounding system where all grounding conductors are connected to a single grounding electrode. It's also important to avoid creating ground loops, which can occur when there are multiple paths for current to flow in a grounding system. Ground loops can be prevented by using isolated ground planes and by ensuring that all grounding conductors are properly shielded. In addition to the NEC requirements, there are also industry standards and best practices for grounding and bonding. These standards and best practices can provide additional guidance on how to design and install effective grounding systems. Some of the relevant industry standards include the Institute of Electrical and Electronics Engineers, or IEE, Standard 142, Recommended Practice for Grounding of Industrial and Commercial Power Systems, and the Telecommunications Industry Association, or TIA, Standard 607, Generic Telecommunications Bonding and Grounding for Customer Premises. These standards provide detailed information on grounding and bonding techniques, as well as guidance on how to select and install grounding equipment. By following these industry standards and best practices, you can ensure that your grounding system is designed and installed to the highest standards of safety and performance. Finally, it's important to remember that grounding and bonding are not one-time tasks. Grounding systems should be inspected and tested regularly to ensure that they are still functioning properly. Grounding connections can corrode over time, and grounding electrodes can become less effective. Regular inspection and testing can help to identify any potential problems before they become serious. The frequency of inspection and testing will depend on the environment and the type of equipment being grounded. In harsh environments such as coastal areas or industrial facilities, grounding systems may need to be inspected and tested more frequently. By following these guidelines, you can ensure that your grounding system remains effective and provides continuous protection against electrical hazards.